Hello viewers, welcome back to the course on scientific computing using MATLAB. So, in the previous lecture we have discussed that if we have a non-uniform distributed nodal points, then how we can approximate a unique interpolating polynomials based on those nodal values. So, today we will continue with this one and we will discuss the Lagrange interpolation polynomials. So, today I am going to use that how to find the Lagrange interpolating polynomial. So, I know that suppose I have some data points that is given to me. So, suppose this is my x0, y0, this is my x1, y1, then I have here x2, y2, this is xi minus 1, xi plus 1, and then I have xn, yn. So, this is n plus 1 data points are given to me, and then based on this one, so these points, if you see, this is given here, this is here, then this is here, then this is here. So, these nodal points x0, x1, x0, x1, x2, xn are not equispaced. So, in this case I want to find the interpolating polynomial such that that is passing through all these points. So, it is passing through all these points, and that unique interpolating polynomial I want to find. So, let us start with the expression. So, I will take the case 1. So, in the case 1 I will talk about first of all linear interpolation. So, in this case I have only 2 points that is given to me. So, this is one point x0, y0, and this is another point that is x1, y1. So, this is my interpolating polynomial. So, I define the let, I define the p1x, that is interpolating polynomial, as e0 plus e1x, a1x, a0 plus a1x. Now, this is the interpolating polynomial, so it should pass through the points. So, if I put x0, so it should be a0 plus a1 x0, and that should be equal to y0, and then I define p1 at x1, so that is a0 plus a1 x1, and that should be equal to y1. So, this is the corresponding 2 equation I get from here, and this can be written as a system of equation. So, this expression I can write in the form of a matrix form. So, this is 1 x0 and 1 x1, and this is the a0 and a1, and on the right hand side I have the value that is known to us at the point of x0 and y0. So, this is the system I want to solve for linear interpolation. So, in this case I know that this is my matrix A. So, and this, the determinant of this matrix is x1 minus x0. So, I know that x0 and x1 are distinct point. So, it means that this matrix is a non-singular matrix. Now, I can solve this one with the help of a inverse of the given matrix, and so this can be written as inverse and y0, y1. Now, from here I know that 1 x0, 1 x1, the inverse of this matrix is equivalent to, so this one I can write the determinant and the, so the determinant of this matrix is x1 minus x0, and the adjoint of this matrix is coming, that is x1 minus x0 minus 1 and 1. So, this is 1. So, now based on this one I get my solution A0 and A1. So, that is equal to x1 minus x0, x1 minus x0 minus 1 1, and that is y0 y1. So, from here if I write down the form, so this becomes x1 y0 minus x0 y1 divided by x1 minus x0. So, this is the first row I am doing. So, in the second one I will get minus y0 plus y1 by x1 minus x0. So, from here I can get the value of a0. So, that is x1 y0 minus x0 y1 divided by x1 minus x0, and a1 is y1 minus y0 x1 minus x0. So, this is the value I am getting, minus x0. Now, if I substitute this value in the given expression, then my linear polynomial p1x can be written as x1 y0 minus x0 y1 x1 minus x0 plus a1 x1 minus x0 into x. Now, if I want to verify that whether it is satisfying the interpolating polynomial properties or not, that at the nodal points its value should be same. So, if I put p1 x0, so in this case this expression actually can be written in this form also, 1 over x1 minus x0. So, y0 I can take common. So, from here this become x1 and from here minus x. So, it will become x1 minus x y0 plus, and this y1 I can take common. So, this will be x minus x0 y1. So, this can be written like this also. So, from here I can see very clearly that if I put x is equal to x0, then this will cancel out and this will be x0, and this x1 minus x0 will cancel out and I will get y0. And if I put x is equal to x1, in that case this will be 0, this value will be 0, and then from here x1 minus x0, this will cancel it, I will get y1. So, that is the corresponding interpolating polynomial. So, this interpolating polynomial generally we will write directly looking at the points, we can write this polynomial as p1x is equal to x minus x1 divided by x0 minus x1. So, this I can write here y0 plus x minus x0 divided by x1 minus x0 y1. So, I am writing the coefficient of y0. So, I put x minus x1 divided by x0 minus x1. So, this expression is same, only difference is that if I put x is equal to x0 here, then this will cancel out and become 1. Similarly, I am putting the coefficient of y1. So, I will leaving the coefficient of y1 and taking the another one. So, it will be x minus x0 divided by x1 minus x0. So, that is the expression for linear, the Lagrange linear interpolation, interpolating polynomial. Now, the coefficient, this coefficient and this coefficient, they have some specific names. So, I can write my expression p1x is equal to L1. 1 means it is a linear function defined at x0, y0 plus L1 1 at x y1, where L10x is this expression x minus x1 divided by x0 minus x1, and L11 is equal to x minus x0 x1 minus x0. So, these two factors are called Lagrange's fundamental polynomial. So, these fundamental polynomials has some properties. So, from here I can write that this fundamental polynomials has some property. So, from here I can write that also if I put L10x plus L11x, so if I am adding all these together, so I will get from here x minus x1 plus x minus x0 x1 minus x0, and from here I will get this value. So, x1 minus x0 I can take common. So, this will be minus x plus x1 plus x minus x0. So, this x will cancel out, and x1 minus x0 this will also cancel out. So, its value will be 1. So, from here that the sum of these Lagrangian polynomials, that value is equal to 1 also. So, this is the first property. The second property is that L10, so it is the interpolating polynomial, the fundamental polynomial, the linear and defined at 0. So, if I put x0, its value should be 1, and if I put L0 x1, its value should be 0. Similarly, 1 x0 it should be 0, and L11 at x1 it should be 1. So, from here I can write that any Li, so if I am talking about this one, so I can write that L, so I am talking about the linear only. So, Li xj, so this is equal to delta ij. So, that is equal to 1 when I is equal to j and 0 when I is not equal to j. So, that is the expression for the fundamental Lagrange fundamental polynomials. So, this is the properties we have to keep in mind for the Lagrangian fundamental polynomials. So, based on this one, so this is the we have defined only for 2 points. The similarly, suppose I have 3 points that is given to me, 1 point is here, 1 point is here, and 1 point is here. So, this is my x0, y0 and x2, y2. So, only 3 points are given to me. So, in this case, if I want to find the interpolating polynomial, so this will be like this one. So, in this case, I will define the second order Lagrange interpolating polynomial. So, in this case we have 3 points. So, I will try to write down the equation, the quadratic polynomial directly, like here from the taking that here I am defining the point coefficient of y0. So, I am taking all the other point except x0. Here I am taking all the point except x1. So, now from here that we have the points x0, x1 and x2, such that I will define that x0 is less than x2, x1 and x2. So, we are taking in the ascending order. Now, from here I want to write the quadratic polynomial, because this will passing through 3 points. So, we can define the quadratic polynomial. So, I will write that p2x. So, in the form of p2x, I can start with this a0 plus a1x plus a2x square, and then I am defining the properties of this one. So P2 at x0 is a0 plus a1 x0 plus a2 x0 square, and that is equal to y0. Similarly, P2 x1 is equal to a0 a1 x1 a2 x1 square, that is equal to y1. And P2 x2, that is a0 plus a1 x2 plus a2 x2 whole square, that is equal to y2. And now from here I will get this matrix. So this is 1 x0 x0 square, 1 x1 x1 square, 1 x2 x2 square, and writing the expression for a0 a1 a2, and this is my y0 y1 y2. So this is the corresponding system of equation we are getting. And now if we solve this one, then I can write, so after solving the same way we can solve. So after solving this system of equations, we get, and now from here I can write my P2x directly. So this should be equal to, now I have a point x0 x1 x2. So I am writing the coefficient corresponding to x0. So I will leave x0 and I will write x minus x1 into x minus x2, and then I put x0 minus x1 x2, and then this is equal to y0. Now I write the coefficient of y1. So I will leave the x1. So I will write x minus x0, x minus x2, and then I put x1 minus x0 and x1 minus x2, and that is y1, plus x minus x0, x minus x1 divided by x2 minus x0 and x2 minus x1, and that is y2. So that is the quadratic polynomial, interpolating polynomial we can write directly with the help of the previous example, the linear interpolation. So this will be the quadratic polynomial, interpolating polynomial, and from here I can write that this will be L20x. So that is a fundamental interpolating polynomial. This is L21x, and this expression is L22x. So from here we can verify that L20x plus L21x plus L22x, that is equal to 1 if I take the sum of this one. And also from here I can see that L20 x0, if I am putting x equal to x0 here, this will cancel out, so its value will be 1, and L20 x1, so x1 is x1, so it will be 0, and L20 x2, that will be also 0. So from here you can say that this is also satisfying the second property of this delta function we have defined. So based on this one we can write the quadratic interpolating polynomial which satisfying whose coefficient as a fundamental Lagrangian polynomial satisfy the corresponding conditions for the coefficients. So from here now I will try to write down the general Lagrange interpolation. So now we can write a nth degree Lagrange interpolating polynomial. So now we have a x0, x1, x2 up to xn. So these are the values, nodal values that is given to me. Now I can rearrange this form in the ascending order, because this is non-uniformly distributed. So I can rearrange that one in this ascending order form. Now based on this one, I want to define the nth order. So Pn I can write. So Pnx will be, I am writing the coefficient of x0. So I will write x minus x1, x minus x2, x minus xn divided by x0 minus x1, x0 minus x2, and in the end x0 minus xn. y0 plus x minus x0, x minus x2 and x minus xn divided by x1 minus x0, x1 minus x2 and this x1 minus xn. This is equal to y1 plus so in the if I go the ith one, I can write as x minus x0, x minus x1, x minus xi minus 1, x minus xi plus 1 and x minus xn divided by xi minus x0, xi minus x1, xi minus xi minus 1, xi minus xi plus 1 and in the end xi minus xn. This is corresponding to the yi. So in the end I will get minus x minus x0, x minus x1 up to x minus xn minus 1 divided by xn minus x0, xn minus x1 and xn minus xn minus 1, that is equal to y. So based on this one, I am able to write the nth degree Lagrange interpolating polynomial, where I can define my expression L nth degree polynomial for any kth coefficient. So this is equal to x minus x naught xk plus 1 x minus xn, and it is divided by xk minus x0, xk minus x1, xk minus xk minus 1, xk minus xk plus 1, xk minus xn. So that will be the any kth fundamental Lagrange polynomial we can write directly, and this can be also written in the form of, so I can write this as a x minus xi product I am taking I from 0 to n and I is not equal to k divided by in the product of x k minus xi. From here I am getting I from 0 to n and I is not equal to k. So this expression I can write in the directly for the Lagrange polynomial. So this is the way we can define the fundamental Lagrangian interpolating polynomial. Now we want to define from here the error involved. So error involved in the Lagrange interpolating polynomial. So we know that in the previous cases also the error involved, I have written the Rx. So, Rx can be written as x minus x naught. So, these are all the nodal values. This value is written at the nodal value x0, x1, and from here it is equal to f n plus 1 xi over n plus 1 factorial, where this xi belongs to any value between x0 to x1. So, in this case also, if I know the value of the function, I take its n plus 1th derivative, and then there is some xi exists in between such that this value is given to me. So, that is the error we can find, and if I take this maximum value of this, then this is the maximum involved in this one. Okay. So, this is the way we can find the error involved in the Lagrange interpolating polynomial. So, after doing this all this expression, we want to define the drawback of this one. So, what is the drawback here? The first one is that for moderately large number of data points, that is when n is quite large, then we have to approximate, or we have to constitute higher degree polynomial which is computationally very costly. So, which is a computationally very costly. It means that suppose I have n is equal to 100, then we have to constitute. So, n is the number of points, we suppose 100, then we have to constitute 99th degree polynomial. And finding the 99th degree polynomial is quite expensive in the terms of computations. So, that is the drawback, that we have if a large value of data is given to us, then it is very difficult to write the higher degree polynomials. The second one is that if for each one additional tabular value whole of the computation is to be done again. Like we have the 5 points, suppose my 5 points are given to me x0, x1, x2, x3 and x4. So, these 5 points are given to me, and I will, based on this one, I will constitute the interpolating polynomial, 4th degree polynomial. Then somebody asked me that, okay, we add one more point and let us add this one. So, now we have a 6 points. So, in this case I have to constitute the whole process again, so that I should be able to write the 5th degree interpolating polynomial now. So, if I add just one point, then the whole process we have to repeat. So, that is why if we add one point, then the same process will be repeated, and again the whole computational we have to do again and again. So, that cost me a lot. So, that is it can be told that it is a computationally costly. So, that is the another drawback of this one. So, first drawback was that higher degree polynomial, and second drawback was this one, that adding one more points needs the whole the process repeat again. So, let us stop today here. So, today we have started with the linear Lagrange interpolating polynomial, and then based on this one we have discussed the quadratic and the nth degree Lagrange interpolating polynomial. So, in the next class also we will continue with this one. So, thanks for watching this lecture. Thanks very much.